Welcome to the 9th session of this integration series. In this session, we will demonstrate various integrals using the technique of integration by parts. The integrands involve the power of sine, cosine, sec, and cosec functions, as well as the transformation from product form to its corresponding addition form. There are 10 worked examples illustrated in this session. Integration is an art form which requires much practice. It is important to learn to recognize the different forms of integrals and to quickly determine the most suitable method. The worked examples in this session contain a mixture of all integral types. Some questions can be solved using more than one method, and it is for you to determine the most efficient method to use.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the 9th session of this integration series. As we can see in example 1, we will find two general solutions for antiderivatives. As for the first one, the antiderivative can be written to the integral of x squared sine of x squared multiplies x dx, which equals 1 over 2 times the integral of x squared sine of x squared with respect to x squared. Accordingly, we let u equals x squared, so the derivative can be written to 1 over 2 times the integral of t sine t dt. Then we use the technique of integration by parts, assuming u equals t, dv equals sine t dt. That led to du equals dt and v equals negative cos t. Hence, 1 over 2 times the integral of t sine t dt equals 1 over 2 times negative t cos t plus the integral of cos t dt, or in parentheses, which equals negative t cos t over 2 plus sine t over 2 plus c. After substituting t for x, we have the general solution for the antiderivative, which equals negative x squared cos of x squared over 2 plus sine of x squared over 2 plus c. As for the second antiderivative, we let u equals ln of x and dv equals dx. That led to du equals 1 over x dx and v equals x. Hence, according to the rule of integration by parts, the antiderivative can be written to x ln of x minus the integral of x times 1 over x dx, which equals x ln of x minus x plus c. Example 2 is to find the general solution of the integral of x times cos squared of x dx. Since the antiderivative can be written to the integral of x times 1 plus cos x all over 2 dx, which equals 1 over 2 times the integral of x dx plus 1 over 2 times the integral of x cos 2x dx. At this point, we apply the technique of integration by parts here to find the term of 1 over 2 times the integral of x cos 2x dx. We let u equals x, dv equals cos 2x dx. That lead to du equals dx and v equals sine 2x over 2. Hence, 1 over 2 times the integral of x cos 2x dx can be written to x sine 2x over 4 minus 1 over 4 times the integral of sine 2x dx, which equals x sine 2x over 4 plus cos 2x over 8 plus c1. Therefore, the general solution of the antiderivative equals x squared over 4 plus x sine 2x over 4 plus cos 2x over 8 plus c. Example 3 here is to find a general solution of the integral of sec cubed of x dx. The antiderivative obviously can be written to the integral of sec of x times sec squared of x dx. Since the differentiation of tan x is sec squared of x, hence we let u equals sec x and dv equals sec squared of x dx. That lead to du equals tan x sec x dx and v equals tan x. So the antiderivative can be written to sec x tan x minus the integral of tan squared of x sec x dx, which equals sec x tan x minus the integral of sec squared of x minus 1, or in parentheses times sec x dx, which equals sec x tan x plus the integral of sec x dx minus the integral of sec cubed of x dx. Since the integral of sec x dx equals ln of the modulus of the sum of sec x plus tan x, the antiderivative is now written to sec x tan x plus the integral of sec x dx minus the integral of sec cubed of x dx. Finally, the antiderivative equals 1 over 2 multiplies the sum of sec x tan x plus ln of the modulus of the sum of sec x and tan x, or in parentheses plus c. Let's look at another example. In example 4, we are going to find a general solution of the integral of the cosec to the fourth of x dx. Since the integrand can be written to cosec squared of x times itself, which equals cosec squared of x times cotangent squared of x plus 1, or in parentheses dx, which can be written to the integral of cosec squared of x dx plus the integral of cosec squared of x cotangent squared of x dx. In the meantime, since the differentiation of cotangent x equals negative cosec squared of x, which gives d cotangent x equals negative cosec squared of x dx, hence the antiderivative is written to negative cotangent x minus the integral of cotangent squared of x d cotangent x, which equals negative cotangent x minus cotangent cubed of x over 3 plus c. Example 5 is to find a general solution of the integral of sine 2x sine 3x dx. Since the product form of circular functions can be transformed to its corresponding addition form, the integrand function sine 2x sine 3x is transformed now to 1 over 2 times cosine x minus cos 5x, or in parentheses. Hence the antiderivative equals 1 over 2 times the integral of cos x minus cos 5x, or in parentheses dx, which equals sine x over 2 minus sine 5x over 10 plus c, after the anti-differentiation being performed. Example 6 here is to find the antiderivative of the integral of cos 2x over cos x dx. Since the integrand can be written to 2 cos squared of x minus 1 all over cos x, it can be simplified to 2 cos x minus 1 over cos x. Since the integral of 1 over cos x dx can be written to the integral of 1 over 1 minus sine squared of x d sine x, which equals 1 over 2 times the integral of 1 over 1 plus sine x plus 1 over 1 minus sine x d sine x. After being integrated, it equals 1 over 2 times ln of 1 plus sine x minus ln of 1 minus sine x, or in parentheses, which can be further simplified to ln of modulus of sec x plus tan x plus a constant c1. Next time when encounter the integral of 1 over cos x dx, we will use this result straight away. Hence, the antiderivative is written to the integral of 2 cos x minus 1 over cos x, or in parentheses dx, which equals 2 sine x plus ln of the modulus of sec x plus tan x plus c. Example 7 here is to find the antiderivative of the integral of cos x plus sine x, or in parentheses cubed over the sum of sine 2x plus 1 dx. Since sine 2x plus 1 can be written to sine squared of x plus 2 sine x cos x plus cosine squared of x, which equals sine x plus cos x, or in parentheses squared. Hence, the antiderivative can be written to the integral of cos x plus sine x, or in parentheses cubed, over cos x plus sine x, or in parentheses squared dx, which equals the integral of cos x plus sine x, or in parentheses dx, which equals sine x minus cos x plus c. Example 8 here is to prove the integral of sine x sine 2x dx equals 2 sine cubed of x over 3 plus c. Since the product form of circular functions can be transformed to the corresponding addition form, sine x sine 2x is then transformed to cos x minus cos 3x all over 2. Since sine 3x can be written to sine 2x plus x, which equals sine 2x cos x, plus cos 2x sine x, which can be further simplified to 3 sine x minus 4 sine cubed of x. Hence, the left-hand side equals the integral of cos x minus cos 3x all over 2 dx, which equals sine x over 2 minus sine 3x over 6 plus c, which equals sine x over 2 minus 3 sine x minus 4 sine cubed of x all over 6 plus c, which is simplified to 2 sine cubed of x over 3 plus c, which is exactly the form on the right hand side. Here, example 9 is to find the antiderivative of square root of 1 plus sine x over sec x dx. First of all, the antiderivative can be written to the integral of square root of 1 plus sine x times cos x dx. Since the differentiation of sine x equals cos x, which gives d sine x equals cos x dx, hence the antiderivative is written to the integral of square root of 1 plus sine x d sine x, which equals 2/3 times 1 plus sine x, or in parentheses to the power of 3 over 2 plus c. The last example in this session is to find the antiderivative of the integral of square root of 1 plus sine x dx. Since 1 plus sine x can be written to sine squared of x over 2 plus 2 sine x over 2 cos x over 2 plus cos squared of x over 2, which equals sine x over 2 plus cos x over 2, all in parentheses squared. Hence, the antiderivative equals the integral of sine x over 2 plus cos x over 2, all in parentheses dx, which equals negative 2 cos x over 2 plus 2 sine x over 2 plus c. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.